So now we understand how to measure the formal potential, the potential at which an atom or a molecule is in equilibrium with its corresponding ion through a reduction process. The higher this potential, the more negative you have to make the atom or molecule in order to reduce it, the easier it is to oxidize, and thus things that take a high potential to reduce will tend to give electrons to things that are lower down that list of reduction potentials. We measure these formal potentials either in a static measurement with respect to a reference electrode or with a linear sweep voltammogram, as explained in the last module. So now we turn to understand the Averym-Ratner diode and that potential difference of 1.12 volts for driving the electrons in one direction through the device. The two components used in the rectifier were the donor tetrathiophulvalene and the acceptor tetracyanquinone dimethane. So let's take a look at these guys. The TTF contains sulfurs in the ring that tend to donate electron density to the ring, and this makes it easy to oxidize. So TTF is readily driven into the form TTF plus with a 1 electron oxidation. This is a radical because electrons like to come and leave in pairs and unstable, so a second oxidation takes it quickly to the state TTF2+, which is a stable ion. Conversely, TCNQ has these electron withdrawing groups, these cyano groups, and for that reason the quinone ring is easily reduced. It likes to accept electrons from a donor, and correspondingly it's very hard to oxidize. So let's take a look again at the Averym-Ratner diode with this in mind. So with the TTF next to the negative electrode, the TTF can readily donate electrons to the TCNQ because it is easily oxidized, and then with this electrode biased high enough, accept electrons from the electrode to go back to its neutral form. Conversely, the TCNQ will readily donate electrons to this electrode if its bias is positive enough, i.e. this Fermi level lies below the level needed to accept electrons from it, and so it will then start off in the TCNQ2+ mode. It will readily accept 2 electrons from the TTF, and that will then make it neutral TCNQ, but because of the very high positive bias on this electrode here, this will instantly cycle back to TCNQ2+. So the electrodes then, with this particular arrangement of bias, here a very high negative bias to sweep the TTF2+ back to TTF, and here to sweep the TCNQ2+ back to TCNQ. The overall reaction that occurs in this diode then, by this electron transfer step in the middle, is TCNQ2+ and TTF on the right electrode becomes TCNQ on the left electrode and TTF2+ on the right electrode. And the question is, what is the driving free energy for this reaction? Well, this is something we are going to work out given a set of data for the individual steps in the 1 electron reduction reactions of the components involved in this. They are listed on the table here, and I've copied them out here again because we'll use them on the next slide. One comment, all of these of course are potentials with respect to the normal hydrogen electrode. We will work out differences in potential, so the use of a reference electrode, then particular reference electrode becomes immaterial. We're then left with a difference in potential, which we turn into a free energy using this expression here, minus delta G is the number of electrons involved. We'll deal with 1 electron reactions always, times the Faraday, the number of coulombs in a mole, then times whatever this potential difference is. So let's go ahead then and use these data that we can find in the published literature for the components of this step, and let's work out the overall reaction here that describes the electron transfer within the rectifier. Now we are given not this reaction, but steps in it. So let's start with this first piece of data we are given. TTF plus an electron goes to TTF at plus 0.37 volts. We can find the reverse reaction, which is TTF giving up an electron to become TTF plus, if we change the sign of the standard potential. And this is done here. We can then take our data for TTF2 plus an electron going to TTF1 plus at minus 0.05 volts, and once again find the reverse reaction, TTF plus going to TTF2 plus plus an electron by reversing the sign of the bias, and this is done here. So if we now add these equations together and cancel common terms, so you see here we have a TTF plus and a TTF on the left and a TTF plus on the right, we are left then, by summing these together, with an overall expression for TTF going to TTF2 plus 2 electrons. And by summing these two potentials here, we end up with E0 is minus 0.32 volts. Now, let's go to the reactions involving a TCNQ. So we are given one reduction reaction here, which in fact we need. We don't have to change the sign of anything since this is now a reduction reaction. TCNQ 1 plus an electron goes to TCNQ at plus 0.54 volts, so we've placed this here. And then finally we're given TCNQ plus 2 plus an electron goes to TCNQ 1 plus at 0.9 volts. We can add these two reactions together and cancel the components that are in common on the left and the right, since they contribute the same amount to the free energy. So we cancel the TCNQ1 pluses on both sides, and we have this overall reaction here, TCNQ2 plus 2E goes to TCNQ. Finally, we can add reaction A and reaction B and cancel the common term, which is the 2E on the left and the right, and we're left with the overall desired reaction, TCNQ2 plus TTF goes to TCNQ plus TTF2 plus. This then, by summing these two potentials here, gives us the overall driving potential for the reaction at 1.12 volts, which was stated at the beginning of chapter 8. So in one direction, the reaction rate is proportional to e to the minus 1.12 volts divided by a 40th of a volt, or e to the minus 40. That would be the back reaction, moving the electron from the acceptor to the donor, and that is essentially a rate of 0. In the forward direction, the rate is, of course, extremely high. So this explains how the Averym-Ratner diode works. One can use data like this to design molecules and the direction of electron transfer within molecules. If you read section 8.9.5 of the book, you will see how electrochemical data were used to design the light-to-charge converter molecule, so making sure that the keratin on one side donates an electron to the ground state of the excited porphyrin, while the buckyball on the other accepts an electron from the excited state of the porphyrin. Actually, the expression for the electron transfer rates is not simply an exponential of the free energy divided by kT, as I seem to imply in the discussion we just had. It's a little more complicated than that, but we will turn to the correct expression for electron transfer rates as a function of free energy in the next module.